Dear students, welcome to this chemistry lecture series. In this lecture, I am going to cover isomerism in coordination compounds. As you know that isomers have the same molecular formula and their atoms are arranged either in a different order, which means different fashion, which leads to structural isomers. And also, these atoms can be arranged in a different spatial orientation or different spatial arrangement. So that leads to stereoisomers. These two categories we will discuss in this lecture. Let's see some classes of isomers. As you can see from this slide, that from this flow chart, that isomers have same chemical composition but different bonding and properties. Isomers can be majorly classified into two types. One is structural isomers and the other one is stereoisomers. Structural isomers differ in their bonds. Let's see the types. There are four types of structural isomers. One is ionization isomerism, hydrate isomerism, coordination isomerism, and linkage isomerism. So we will see one example for each type, and we will see how this isomerism occurs. And also the other type of isomers are stereoisomers. They have the same bonds, whereas structural isomers have different bonds. Stereoisomers have same bonds and different spatial arrangement. There are two major types of stereoisomers. One is geometric isomers and optical isomers. The property is called geometric isomerism and optical isomerism. Specifically, we will discuss about the cis-trans isomerism and geometric isomerism. Let's discuss about the structural isomerism. As we seen in the flow chart in the previous slide, structural isomerism are of four types: ionization isomerism, hydrate isomerism, coordination isomerism, and linkage isomerism. This is one of the important uh, essay type question which they will ask in the CT1 and also in the main exam. So we will also discuss about other type of isomerism in organic compounds in unit 3. But so you shouldn't confuse with this coordination isomerism and the isomerism in the organic compounds. Okay, so now let's move on to the examples and what is meant by ionization isomerism. As you can see that these isomers have same overall composition, but the composition of the coordination sphere will vary. So the main difference will be the ions present inside and outside the coordination sphere. Some isomers can also differ in the ligands that are bonded to the metal and what is outside the coordination sphere. As a result, these are also called coordination sphere isomers. See these two coordination complexes. These are the example for ionization isomerism. These two complexes have metal ion chromium, so it's a they are chromium complexes. And what are the ligands? They have 5 amine ligand and 1 sulfate ligand. And the counter ion is bromide in the previous case, and the counter ion is sulfate in the later case. So the ion I have highlighted in bold so that you can understand the difference. So what is the difference? Look at this one. Metal ion is same. The amine ligand, 5 amine ligands are same, but only the sulfate ion and sulfate ion is interchanged with the bromide ion. As a result, the counter ion are also interchanged. To keep it simple, in the ionization isomerism, the counter ions are different. In the former, the sulfate coordinates to the metal and bromide is the counter ion. In the later one, opposite happens. So when you dissolve these complexes in water, upon dissolution in water, we get bromide ion in the former case, whereas we will get the sulfate anion in the later case. So when you write this essay type question, just write about what is ionization isomerism, give these two examples and mention the difference. Okay. The counter ion should be different. That is the key point. So don't miss that one. And then let's see the second type, that is hydrate or solvate isomerism. Hydrate means from the name itself you can tell that water molecules. So the number of water molecules present outside the coordination sphere will vary. So this leads to hydrate or solvate isomerism. So three isomers of chromium. So I have given the same chromium like the previous case so that it will be easy for you to keep in mind. So CrCl3 H2O6. So aqua ligand, hexa aqua ligand is present, and Cl3 is the counter ion. So now what we are going to do, this complex, particularly this aqua ligand containing complex, all six are aqua ligand. So it is an octahedral complex. So the color will be violet. When one of the aqua ligand is replaced with the chloride ion, then in the previous case, you are having three chloride counter ion. So one of the chloride counter ion will be replaced with water. So when you dissolve this complex in water, you will get two chloride ions and one aqua, that is water, in the solution. The hydrated one also will dissociate, and also this complex ion as such it will be present in the solution. The color of this complex is green. The other type is, let's see, like instead of having 5 aqua ligand, we will have 4 aqua ligand and 2 chloride ion and 1 chloride will be present. As a result, 2 water molecules will be present outside. So this is an example for, these are the examples for hydrate or solvate isomerism. Now let's see the next type, coordination isomerism. They differ in their coordination entities, which means the coordination, the counter ion will also be a coordination sphere, and their coordination entities will be different. Let's see the example. For example, let's take this one. So when both the positive and negative ions are complex ions, then that type of coordination isomerism, that type of isomerism is called coordination isomerism. This isomerism may be caused by the interchange of ligands between the anion and cation. So let's see this one. So what is the, as I said, both positive and negative ions are complex ions. So here you have cobalt NH3 3 plus, and here you have Cr CN6 3 minus. So here the interchange of ligands have happened. Also the metal ions are interchanged. So the cobalt replaced with chromium, and the ligands amine is replaced with the cyanide, and this is also an octahedral complex. Similarly, you can also write this type of ion. Look at here, this cobalt is interchanged with the chromium. As a result, in the previous case, cobalt is bounded with the amine ligand. Now, the chromium is bounded with the amine ligand. Just interchange, we have interchange. And similarly, for the cyanide, chromium metal ion has been bound. Here cobalt metal ion has been bound. So this is how the coordination isomerism will happen. They have same total composition, but they have different complex entities or complex ion. So another example also I have given here for zinc, that is with coordination number 4, NH34, zinc and CuCl4. Here also you can interchange zinc with copper, so you will get copper NH34, and instead of copper you can interchange with zinc and you will get ZnCl4. These are also called as coordination isomers. Why? Because both the positive and negative ions are complex ions, and the isomerism is caused by the interchange of ligands between the anion and cation. Now let's discuss about the third type of isomerism, that is linkage isomerism. So in this one, in the previous case, the composition is different. Here the composition of the complex ion is the same. But what would be the difference? The point of attachment of at least one of the ligands differs. For instance, we will take a ligand like nitro and nitrito. Here, in the case of nitro, the point of contact with the metal ion will be through the nitrogen atom, whereas in nitrito, the point of contact will be through the oxygen atom. So this is an octahedral complex with coordination number 6. So 4 amine ligands are present in the same plane. Fifth one is present below the plane, and the sixth one, nitro, is present above the plane, which is coordinated with the metal ion, which is represented in green color, that is cobalt, through the nitrogen atom. Whereas the same thing on your right, you can see that the same nitro ligand we have rearranged, and the oxygen atom is coordinated with cobalt ion. So we call nitro ligand. And the color of the nitro ligand coordinated complex is pale brown, which is little bit deep orangish brown, you can say, for nitro. So these are the two simple examples for linkage isomerism. Same ligand, but the donor atom is different. Another example, the well-known example, is thiocyanate and isothiocyanate. Thiocyanate means SCN minus, isothiocyanate means NCS minus. Again, we take the cobalt. The previous two isomerism, we take chromium. For linkage, we are taking cobalt. Just remember, cobalt. And again, same thing. You just look at here, all the 5 are amine ligand. The sixth one above the plane, we are putting the SCN ligand, which is violet in color, and for the other one, NCS, we have changed. The point of contact is nitrogen. In the previous case, it is sulfur. As a result, the color of the complex also changes. When it is coordinated through sulfur ligand, the color is violet, and when it is coordinated through nitrogen, it is orange. So these linkage isomers are violet color and orange color. Okay. And now let's move on to the structural isomerism. We have done stereoisomers. We are going to discuss geometrical isomers. So geometrical isomers are most important for square planar and octahedral complex, but specifically we will discuss about the octahedral complex. So we will see isomerism in octahedral complexes. Only one structure is possible for octahedral complex when one of the ligand is different from the other. This is the general formula Ma6, but instead of the sixth A ligand, you are replacing with B. So one of the ligand is different from the other 5. So the all 6 vertices of an octahedron are equal. Look at here, the cyan ones represent the A atom. So 4 A atoms are present in the plane. Fifth atom is present below the plane, whereas the one atom, that is B, different from the A, is represented with the purple color, that is B. So the corresponding structure is written next to the this octahedral shape, like 4A present in the same plane, fifth one below the plane, and the B atom is present above the plane. So the it satisfies the general formula Ma5 B type octahedral complex. And what is the other possibility? Whether you write the B above the plane or below the plane will be same. But instead of writing above the plane, you can have this B type ligand in any one vertices or corner of this square planar structure. So I have put the B here. So here the bonds are written by dark wedge shaped bond and dotted lines. In stereochemistry, you should remember this dark shaded wedge shaped bonds represent the atoms or ligands are facing towards the viewer, and dotted line means they are facing away from they are positioned away from the viewer. And in this structure also you can draw an octahedral shape. When you connect these points, the ligands, you will get an octahedral shape. Here the B atom, the purple one, is different from the all other 5 A atoms. So this is an example for stereoisomer. Okay, now we have seen the Ma5 B type. Now we are going to see Ma4 B2 type, which means 2 B atoms are different from the 4 A atoms. If 2 ligands in an octahedral complex are different from the other 4 A atoms, 2 isomers are possible. So just remember, when only one B atom is different from the 5 atoms, you will not get cis or trans type. Only it is possible when 2 B atoms are different from the 4 A atoms. Then you will get trans and cis isomers. You might have learned this trans and cis before, like when the same groups are present, same atoms or groups or ligands are present on the same side or adjacent to each other, that is called cis. When they are present opposite to each other, that is called trans. Look at this one. So you are having a square planar structure, and three A atoms are present, one B atom is present, which is pointed by wedge-shaped bond, which means it is facing toward the viewer, and one B atom is above the plane, which is also facing toward the viewer. So since they are facing to both B atoms are facing toward the viewer, this belongs to cis isomer type. And what is the other possibility to have the cis isomer? Instead of having one in the plane and one above the plane, the B atom, you can have two B atoms next to each other in the adjacent to each other in the same plane. That is what I have written here. And these both two structures are also cis isomers. And let's move on to the trans isomer. What is trans isomer? As I said before, when the same ligands are present opposite to each other, then it is trans isomer. Look at here in the square planar case, in the same plane, four A atoms are present and the B atoms are present. One is present above the plane, other is present below the plane. So they are opposite to each other in direction. So this complex is called trans isomer. This is equivalent to, instead of having one B atom above and the below the plane, you can also have the B atoms opposite to each other, that is toward the viewer and away from the viewer. When you have these two B atoms in this same square planar shape, that is vertices of the square planar, you can have this type of isomer. Here, look at here, one is facing toward the viewer and the other B atom is facing away from the viewer. So it is a trans type. And you also need to write one example for this one, that is Ma4B2 type. Can you see this? M is the metal ion cobalt, A4 is the Na3 4, and B2 Cl2, and then you have the counter ion fluoride. So this is a cobalt complex, and you have the coordination number 6, so it is an octahedral complex. And in this case, exactly, you write this structure like this. Here, the NH3 ligand is represented by a blue sphere connected with three the hydrogen atoms, which are in white or gray color. Okay, and the cobalt atom is present in the middle, and also you have the chloride ion, which is represented in green color. Okay, so here in this picture itself, you can say the chloride ions are facing toward the viewer and are placed in the same plane. So in the four corners of this square planar structure, you can have two amine ligands and two chloride ligands represented with in pink color, that is adjacent to each other, and they are facing toward the viewer. Obviously, this is cis type. So the red form of cobalt NH3 4 Cl2 plus, and we can also get green form of cobalt Na3 4 Cl2 complex with positive charge, one single positive charge. How? So when the position of these chloride ions are altered, instead of cis positions, you move this chloride ion, one of this chloride ion to the, just interchange Na3 with this chloride, then you will get this structure where the chloride ions, chloride ligands are positioned opposite to each other. Exactly, look at here, the green atoms represent the chloride ligands and they are present opposite to each other. Obviously, this is transformed. So this is the beauty of coordination chemistry. By changing the position of the ligand or the changing the coordinating atoms, whether it is in this adjacent to each other or opposite to each other, the color of the complex can be changed. Same chemical composition, same number of groups of same times are attached to same metal. This is a general description, but when you write this isomerism, stereoisomerism for Ma4B2 type, you can write this example, the cobalt complex. And now we move to the optical isomerism. So isomers have opposite effects on plane polarized light. As you know that when you see the light, it will be moving in all directions. When you have a um, plane polarized, when you have a mirror or a polarizing thing, so, and when you pass this one, the light beam through this one, And when you have your optically active molecule, then when the light beam passing through the solution containing the optically active molecule, whatever the beam coming out now, that will rotate the plane polarized light in either one direction, either clockwise or anti-clockwise. That we know, clockwise means dextro, anti-clockwise means levo. But what is the criteria for the particular coordination compound to be optically active, or a organic compound to be optically active? The main thing is it should have the molecule should be chiral. So what does it mean? So the mirror image should not be non-superimposable. In the other criteria is the four different atoms attached with the carbon should be different. That is the chiral center or chiral molecule. But the main criteria for this coordination compounds to be optically active is that its mirror image should not be superimposable. That is non-superimposable mirror images. They are also called as enantiomers. So the isomers of non-superimposable mirror images. Just to keep it simple, you can't put the right glove in the left hand, just like that. If you have the left hand, then when you show in the mirror, it will exactly look opposite. It will look like right hand, but they are not superimposable. Similarly, look at this picture where you have this nitrogen containing ligand, which is ethylene diamine, and you can see that these two ligands are attached. So the other ligand is, these two ligands are facing toward the viewer. The third ligand is facing away from the viewer. When you keep the mirror, then this will be exactly opposite to that. So whatever the ethylene diamine ligands facing toward the viewer will move away from the viewer, and this one will move towards the viewer. I mean, this one is away from the viewer. Now it has moved toward the viewer. This is toward the viewer, that has moved away from the viewer, and this is also the same thing. So non superimposable images. So you have to write one when you are writing this essay type question. You should also write what is in the optical isomerism. Just write the chiral molecules, non-superimposable. These two criteria you remember uh, to mention, and also how they exhibit geometrical isomerism or optical isomerism. Let's take this one, cobalt En2 Cl2 with the counterion fluoride. So the coordination number is this is 2, and bidentate ligand, so 4. This coordination number is 6, and octahedral complex. Trans and cis isomers we will see. Look at this one. I have drawn the structure of ethylene diamine, where the two nitrogen atoms have, each nitrogen atom have a lone pair of electron which can donate and which can coordinate with the central metal ion. So that's why the single molecule but two nitrogen atoms with lone pair, so they can form the bond with the metal ion. It is called as bidentate ligand. For this type, we can write CO. Ethyl diamine is connected opposite to each other, and the chloride opposite to each other. When you have the mirror, then this exactly it will tilt to the, here it is tilted towards right now, it will tilt to the left, the groups. So when you keep this over this one, it is not superimposable. Uh, this is exactly same. These two forms are identical and also superimposable. So only the trans isomer is possible, and it is optically inactive. Since it is superimposable, it is optically inactive. So even if you keep this one, that this chloride ion will overlap with this one, this will overlap with this one. So it is superimposable. As a result, it is optically inactive. But let's take its this is transform. Am I right? Ethylene group, ethylene diamine is present opposite to each other. Chloride is also present opposite to each other. So obviously transform. Transform is optically inactive. Now let's take the cis form. Here the En groups are present adjacent to each other. In this case, when you put a mirror, exactly you will get the opposite one, and then this one, if you move this molecule on the left and you put it on the right, here you are having the En groups on the left, here you are having the En groups on the right. So it is non-superimposable. So two enantiomers of the cis form are optically active. Just remember, for this complex COEN2Cl2Cl, the cis forms are optically active. Why? Because they are non-superimposable. But whereas the transform is super impossible, so optically inactive. Okay, so with this, the isomerism question, the asset type question, if you write up to that, it is enough. Now, we are almost at the end of the crystal field theory. So I want to conclude the crystal field theory, um, like advantages and disadvantages of crystal field theory. So this is the end of the crystal field theory part. What are the advantages of crystal field theory over the valence band theory? It explains the colors of the complexes. It explains the magnetic properties of the complexes. We have calculated the magnetic moment. So without knowing hybridization and temperature dependence of magnetic moment, calculations or estimations are also possible. It classifies ligands as weak and strong. We have seen the weak ligand, the halogens or halides, and the strong ligand, cyanide and carbonate. So you can classify based on the strength of the ligand. That is what spectrochemical series is about. Now we have discussed that one. And then it explains the anomalies in physical properties of metal complex, like the color and the solubility, etc. And also it explains the distortion in shape. When the ligands are very strong, they can be pushed further apart due to the crystal field splitting, and that can this can lead to distortion in shape for in the metal complexes. The disadvantages or drawbacks, like it evidences for the presence of covalent bonding is not well explained by the crystal field theory. So it does not say anything about hybridization or orbital overlap in metal complexes. The CFT has completely disregarded the hybridization part. It does not explain why carbonyl CO is the carbonyl ligand. Why, although the carbonyl is neutral, is a very strong ligand. There is no explanation for this. And also, it cannot predict the shape of the complexes since it is not based on the hybridization. So most of the structures can be easily explained by hybridization, but CFT disregards the excludes this hybridization part. So it cannot explain the shape of the complexes, whether it is only, it does not explain all the shapes, only tetrahedral and octahedral it can explain, does not explain all the other shapes. Charge transfer spectra not explained by CFT alone. So not only by CFT, we need other theory supports as well. So these are the three limitations of disadvantages of crystal field theory. So you can write three advantages, three disadvantages depending on the question pattern. Okay. So with this lecture, I finished this isomerism part. This is an important essay type question for the first year BTech chemistry student in CT1 and also in the main exam. So practice the this question and also choose the right examples. As I said, the chromium complex and cobalt complex. You can also write other examples, but keep it simple. Just use these two examples and explain this isomerism question. Thank you for listening. I will meet you in the next lecture series. Thank you.